reports out to you, but I'm taking them back. I thought I did have them this weekend, but I thought I didn't have them. So anyway, my dog didn't eat them yet. And I've got 2 sets that I'm hoping to get done tomorrow. So we've been talking about, we're setting ourselves up for thermochemistry, thermodynamic, chemistry problems. We talked a little bit about temperatures and energy, and you had some homework with regard to those 2 things. And remember, thermodynamics, that's the word I was after. Thermodynamics are about tracking the invisible. Basically saying something heat up and knowing it heated up because some energy zapped, some energy was transferred into there. We didn't see the energy, but we saw its effect. So calorimetry is a type of problem, a type of experiment in chemistry where we actually track heat. The other day I kind of brought this up. I said, what if we stick a thermometer in both of these liquids and they're both at 100 degrees Fahrenheit? Not 100 degrees Celsius, that'd be way too hot for a bath. But 100 degrees Fahrenheit, you guys told me the other day that the one that would have more, even though they're at the same temperature, the one that has more thermal energy is the bathtub full of water. Yep, and you're right. So we have these 2 things. We have temperature and thermal energy, and they are not synonymous. Which one of them, temperature or thermal energy, is independent of amount, an intensive property? Temperature is intensive, yep. So intensive. So it starts with the letter E, so what is thermal energy? Extensive. It does depend on amount. And I think I told you the other day that you need to know the T, you need to know the temperature, you need to know the mass. I'll put a little M here, okay? And the third quantity you need to know about the amount of thermal energy an object contains is it's what we call specific heat. There's 3 quantities you need to have a handle on if you're going to point to an object. You're going to say object A has this much thermal energy. This last one, okay, so here we have T, here we have M for amount or mass, usually it's mass, okay. Nature of the object, that is just simply a physical property. Specific heat or specific heat capacity is a physical property of the substance. Water, in the case we're looking at with a cup of water and a bathtub full of water, the specific heat of both those waters is the same thing. Look it up on a table. So what does that physical property mean about matter? The other day when I said the definition of a calorie, remember, and I kind of drew my one little box up here. Okay, I'm going to draw my box up here, and kind of similar to the way that little picture went. I'm going to go ahead and say that I've got 1 gram of substance. 1 gram of substance. It could be water, it could be air, it could be iron, it could be glass, but I have 1 gram, and I'm going to zap it with heat. So we have my zapping with heat is my little squiggly mark there. Okay, heat. I'm going to zap it with a certain amount of heat. Okay. And that amount of heat is, I'll come back to that, but I'm going to raise the temperature up. Do you guys remember what temperature when I talked about the definition of a calorie? It was water, 1 gram of water, raising it from what to what? 14. Yep. From 14.5 to 15.5 degrees Celsius. So 1 degree Celsius. So you figure that if you don't change if you don't change the substance, glass is always going to, 1 gram of glass is always going to require a certain amount of heat to raise it from 14 to 15 degrees Celsius. Liquid water, it's always going to require, 1 gram will always require the same amount of energy. So actually that energy brings us to the specific heat. It's the property. So specific heats are physical properties. They're actually more specific to physical. They are thermodynamic properties of a substance. Thermal properties. The abbreviation for specific heat or specific heat capacity, those mean the same thing. Specific heat or specific heat capacity is C lowercase p. I know in biology, sometimes they look at this physical property of material and they call it specific heat like that. We don't do that. Specific heat is C with a lowercase p, subscript p. That's specific heat. So does this make sense? We talked about units of heat could be joules or metric. Calories are English. So the units are going to be energy per 1 gram of substance per 1 degree Celsius. That's what specific, it's a thermal property. Look it up. So units of energy could be joules or calories per gram, raising it up 1 degree Celsius. My next slide kind of tackles this a little bit, but we talked about temperature scales. What is the cool thing, no pun intended, about degrees, the Celsius and Kelvin scale? What's the relationship? They're offset by 273.15 units, but 1 unit is the same, right? 1 unit is the same. So if here we're talking about one unit on the Celsius scale is equal to 1 unit on the Kelvin scale. So as it turns out, we can kind of use these interchangeably. This is my favorite way to write units of specific heat, but fortunately or otherwise, these are also units of specific heat. These kind of get on my nerves. We're all about factor label, making things cancel that need to cancel, being left with units of things that don't cancel. I don't like this as well as this, okay? Joules per gram per degree Celsius. To me, this is like, almost seems like it, like degree Celsius in the numerator, but you'll see it written like this. And of course, the second one here, anything raised to the negative power is in the denominator, okay? So I'm okay with these, I suppose. You can't really use them for factor label canceling. I don't really like that one. But it is as it is. So this is what I just asked you a minute ago. The relationship between Celsius and Kelvin are both metric, and 1 unit is the same. So we can actually just kind of be swapping out the specific heats as we need to. When they have units per degree Celsius, it's the same thing as units per or energy per gram per Kelvin. So these are some constants of some substances, some materials. The reason they're not substances is because I have air here. Sometimes I will say this specific heat is how stubborn. Sorry. So in other words, these are units of energy per gram for raising the temperature of 1 degree Celsius. So does this make sense? Can you see where helium is pretty darn stubborn? It takes 5 joules, over 5 joules, to raise 1 gram of helium up 1 degree Celsius. Okay. The cool thing about that is helium, once you have that gram of helium heated up, okay, it's stubborn to heat up, and it retains its capacity then to keep that heat is high too. Oxygen, relatively low specific heat. Water, pretty darn high. And in meteorology, actually just the way our planet works, okay, water in its liquid state it's very important that it takes so much energy to budge the temperature of liquid water. Okay? It just does. But that also means, like, when our swimming pools are nice and hot during the daytime, at nighttime they take a long time to cool off. Now it's not just specific heat, but that would be a thermal transfer issue. But its specific heat's very high. All right. Before I move on, do you guys see this? When we talk about thermodynamic problems, you need to make sure that you know what the physical phase is. There's water liquid, water solid, water gas. Okay, those have 3 different specific heats. So don't let that mess you up. Here are some more substances. Let's see, let's pick on what's got a low specific heat. Well, gold, but I don't have much gold, but I probably have lead here and there. Okay, again, a low specific heat means that that material doesn't take much energy before you see its temperature go up. And as it cools down, it doesn't really have much energy to give to anything else. Again, just kind of looking at an assortment of specific heats. Units are always going to be energy per gram per either degrees Celsius or Kelvin. And the numeric value of degrees Celsius or Kelvin would be the same. Some more substances. Yep, here is where you see the liquid water. See water liquid, 4.184, and here it is in solid state. You never know when you're going to need these. Okay, so let's just kind of, I've got a little equation coming up to kind of show you the relationship between zapping energy, the mass that's being zapped, and the temperature change in the thing that's being zapped, and the specific heat of the thing that's being zapped. But if we just kind of think about raising equal masses of 2 different materials to the same final temperature. So we have a specific heat of copper, which is 0.385 joules per gram per degree Celsius, and the specific heat of aluminum is higher. So we are going to bring them to the same final temperature. How many people think we'll have to zap? Which one's going to take more? How many people think the copper will take more? How many people think the aluminum will take more? Why will the aluminum take more?
Because it requires more of a heat thing.
Yep. Because aluminum is more stubborn. Yep. So we're going to actually see how we get that zapping energy in a minute. But Q is energy zapping. Q is energy zapping. Actually in or out. So here we're adding this amount of energy, 6.73 joules, to go ahead and get it up. What is this? What's our change in temperature? If it's going from 20 to 50, what's our change in temperature? 30 degrees, exactly. Yep, 30 degrees Celsius. So same temperature change up here. Yeah, this one is more stubborn. We have to zap it with more energy. It's almost a visual thing. So this is kind of similar, and again, we're going to kind of show you where those numbers come from here in a minute. But in this case, we have, again, the same two substances, listed in the same order, copper with the lower specific heat, and aluminum with the higher specific heat. And now we're going to zap them with equal energy. And the question here is, which one is going to get hotter? How many people think that the copper will get hotter, zapping with the same amount of energy? Oh, you guys are going to find. Why does it get hotter?
It needs less energy to be heated.
It's getting boring. It's got a lower specific heat. It's less stubborn. Yeah. So again, Q is the zapping, the energy. And what's the Q here, by the way? What's that? What's the Q in here?
T sub F.
Nope.
Oh, 500.
Yep.
That makes sense.
I didn't mention it, but yeah, the zapping is 500 joules. How many say figs with that number? Oh, you guys are great. I got the whole figure thing going. Awesome. So if I draw arrows next to these, what does that mean?
They're classics.
They're classics. You have to memorize this. And actually, remember, I think of water as being a little bit anomalous in its liquid form. This is actually water in its liquid state. Water in its liquid state is pretty darn stubborn. Oh, and does this make sense too? Remember Friday when we talked about energy units? We said that there's this exact relationship between joules and calories. And lowercase calorie, remember that's thermodynamic calorie. We said it's 1 calorie is exactly equal to 4.184 joules. Good deal, so memorize those. But are you okay with, and I guess I'm somewhat apologetic because we're really into units here. You're gonna have to think of this as calories per gram Kelvin. And this one is joules per gram Kelvin. Okay, so don't let those slashes mess you up. All right. This is something a little different from the Petrucci book that I most recently taught from. I said Canvas. OpenStax introduces this property of a body. It's called its heat capacity, not to be confused with its specific heat capacity. Or specific heat capacity, specific heat is different than heat capacity. Heat capacity, abbreviated HC, is simply the mass of the object times the specific heat of the object. Which, hey, let's go ahead and do a little factor label here. So if mass is in grams, specific heat could be in joules per gram degrees Celsius. What units would heat capacity be in? Yep, joules per degree Celsius. Perfect. Again, that's assuming that you're not going to be changing its mass. So along those lines, if heat capacity is equal to mass times specific heat, here we have 2 frying pans, cast iron skillets maybe, where we definitely have this mass is less than this mass. Okay, so which one has the highest heat capacity? Yep, the second one.
What does surface area have to do with, like, how it cools down and stuff? Does that have anything to do with that amount of energy that it loses?
No, nope. Surface area, though, your intuition is good because surface area would allow for more places for it to more readily transfer its thermal energy or to gain its thermal energy if you're talking about a hot plate. But the amount of energy it ultimately takes in or gives up is not a function of surface area. So, and actually in this class we don't get into, it's more definitely an engineering problem, the rate at which something will transfer its energy. Cool. So heat capacity, specific heat capacity, they do not mean the same thing. Specific heat capacity, hopefully you're thinking, specific heat capacity, I usually call it just, specific heat. Those are synonyms. And we do this, C sub P. Heat capacity is HC, and that's mass times the specific heat. So you guys were telling me intensive versus extensive properties. So which one, let's see which one is extensive. Which one is extensive? It does depend upon that. Heat capacity. Yep, the whole amount right there. And this one is intensive. It does not depend upon amount. Cool. Well, here finally is a little box. Now, I'll go ahead and put a little arrow here. So that's a relationship that you want to understand. You'll be using it in your problems, that sort of thing. I know some of you have dabbled in the gas law equation, PV is equal to nRT, which we won't get into until Unit 5 in here. But this kind of reminds me of that, in that each one of these variables means something. So of course, Q, I've been saying, is the zapping in, and actually we're going to talk about things don't always take in energy. Sometimes things spit out energy, right? And that would also be the Q. M is the mass of the object that's undergoing the temperature change. This is our first, I think, in here, delta. So delta is the triangle. Anytime you see this, that's the Greek letter delta. And that means change in. So in physical science and in chemistry, we do a lot of deltas, change in. So in this case, we're talking about delta T, change in temperature. And deltas are always going to be final minus initial. Deltas are always going to be final minus initial. Delta, we take the final state, and from that we subtract the initial state. In this case, we're taking the final temperature, and from that we are subtracting the initial temperature. Deltas do have a sign. Our delta T's will have a sign. Okay. So again, kind of like the gas law equation, it's kind of like I talked about being plug and chug. I'm cool with that, plug and chug, but you still have to include all your units and make sure your units cancel and everything. But yeah. The next slide kind of makes sure that it's dimensionally consistent, but Q, we go with joules. Remember, like the 500 with decimal joules, that was our Q. M is going to be in grams. Specific heat, we talked about energy units, in this case with joules per gram, degrees Celsius or Kelvin. And then our delta T is going to be either, the change in temperature is either going to be degrees Celsius or Kelvin. So it looks like this then. So if we go ahead, I'll go ahead and put this over 1. That's my mass over 1. That's my delta T over 1. Units cancel. I got grams cancel with grams. Degrees Celsius cancel with degrees Celsius. Okay, that's what we mean when we say dimensionally consistent. So joules is equal to joules. So not just with delta T's, but delta anything. It's always final minus initial. Final temperature minus initial temperature. And we say final temperatures by putting a little subscript temperature, subscript final, temperature, subscript initial. So what if your sample's heating up? What if final is greater than initial? What will delta T be, positive or negative? Positive, yep. If your final is higher, yep. What if it cools down? What if your final is cooler than your initial? What will delta T be, positive or negative? If delta T, sorry, if your final is smaller, your initial is greater.
Negative.
It would be negative, yep. Now, the way you said it, all sound like Star Trek. Negative, Scotty. Yeah. So there are a few things in physical science where you can blow off the sign, like positive, negative. In that case, actually, what it should be is this is my absolute values. Okay, this is not an absolute value situation. Okay, so you guys answered that right. If your final temperature, notice that I've gone from the whole writing out final just to T sub F. If your final temperature is greater, then that means it's heating up, right? Your delta T is positive. If your final temperature is less than what you started out with, then you're going to be subtracting a larger number from a smaller number, and it's going to be negative, less than 0. Okay, so it's very important. I think I've said that. And the reason it's so important is that, we already did this slide, you okay with this? The reason it's so important is that if you simply look at Q is equal to M C sub P delta T, it's almost like it's got a rap thing going on. When I retire, I'm going to make songs out of science. And no one's going to listen to them, but I will. Q is equal to M C sub P delta T, okay? So masses, what do you think? They're always positive, right? They're always positive. Specific heats, always positive. This can be positive or negative. And that actually then drives the sign of our Q. So this is to say then, if Q is positive, that means our delta T was positive. Check this out. And actually this will help you not just with this subject in Unit 3, but in Unit 3 it's the whole sign thing that kind of drives us nuts. I'll write it up here. So here's my little box, 1 gram of substance, or certain mass anyway. Okay, I am zapping it, so my T sub F is greater than my T sub I. Okay, that means my delta T is positive, and that means my Q is positive. I'm going to go ahead and add a name to that. I'm going to call that endothermic. I know it's not on the slide, I'm kind of getting ahead of myself, but we definitely need to talk about endothermic stuff. Endothermic. Compare and contrast. We can make it the same mass, the same substance, and now what does this mean if I do the squiggly mark out? It's exothermic. Energy's leaving, energy's coming in. In this case, if my T sub F is going to be what? Less than my T sub I. And what does that do to my delta T? Makes it negative. And with a negative delta T, what do I get with my Q? It's also negative. Yep. This, in a nutshell, is what we have going on. This is life. Okay? Something gives up energy, something takes in energy. And in thermodynamics, we watch that. We track that. All right. Oops, what's that? So now Q is equal to MC sub P delta T. It definitely has its limitations. Okay. For instance, you can only use this if the only thing that's happening is the temperature change. You can only use Q is equal to MC sub P delta T. The Q in or out is equal to the mass that's being heated or cooled, the specific heat of the material, and the change of temperature it observes. Okay. This will sum it up as long as there's nothing else happening, which that's not life. Life's more complicated than that, but we're going to pretend that it's not for some of our problems. All right, so let's just assume the only thing that's happening is the little squiggles of energy going in or going out. So I like drawing things. I like it because it's a way to stall. So if I was going to draw this, I would probably draw a little box, and I put my water in my box. So I'll say M is equal to 37.7 grams. I note that it's water. What physical phase is water going to be at both of those temperatures?
Liquid.
Liquid, yep. Not only is water, but we know it's liquid water. So I got a couple temperatures here. See, water originally at 52.0 cooled down to 5.2. So what is our T sub F? Yep, 5.2 degrees Celsius. What's our T sub I? Yep, 52.0 degrees Celsius. So what you're going to see here in a minute is I can do a little subtraction. T sub F minus T sub I gives me my delta T, right? It's always final minus initial. Is my delta T going to be positive or negative? It is going to be negative. So which scenario do we have going on here? Yep. So is the water, how many people think that the water is losing energy? Oh, that's a consensus. What is the energy change of the water? Well, dang, Q is energy change. Q is energy change. So energy change of water, all we gotta do is take the mass, break it into delta T. Now what's the C sub P of liquid water? Yep, that's the one you have to memorize. So the specific heat, C sub P of H2O in its liquid state is 4.184 units of specific heat, in this case going to be joules per gram degrees Celsius. So yeah, I think you kind of see how we're going to work this. But it just kind of helps to doodle sometimes. It gets those little numbers out, and you usually have time in this class anyway to work it. So Q is equal to MC sub P delta T. I'm going after the Q, right? What is the energy change? Anytime a problem asks for energy change, a problem like this anyway, they're asking for Q, energy change. So as, again, I kind of relate you back to, a lot of times students haven't done thermodynamic problems, but they have done gas law problems. And when you did, if you're like me, gas law problems, where you kind of rearrange the gas law equation, you solve for the variable you want to. Variable's already there. So mass, specific heat, you told me, again, that's 4.184 joules per gram degree Celsius. I'm not a fan of this. Grams to degrees Celsius. Delta T is final minus initial. You guys told me the final was 5.2. From that, we're going to subtract 52.0. Notice that this is legit. If both of these quantities, both of these temperatures have the same units, and you're subtracting or adding, you can put the numbers in parentheses and the units outside. That saves you some time. But since we're subtracting, we round according to decimals. So I get 1 decimal, negative 46.8 degrees Celsius. So that's our delta T. And in this class anyway, since I'm a stickler in my instructions for exams to write all units, you need to write all units. So we're going to plug the mass, specific heat, and delta T in, and it looks like this. Q is equal to, I would probably put the mass over 1. Q is equal to 37.7 grams over 1 times the specific heat of water, water in its liquid state, 4.184 joules per gram degrees Celsius times the delta T. And again, I like putting the mass and the delta T over 1, so my units, I can see better what happens with my units. So I'm getting grams to cancel, I'm getting degrees Celsius to cancel, and yeah, change in energy, change in thermal energy, units of joules, I'm good with that. Rounding, how many sig figs? 3. Yep. So change in thermal energy is, we're going to keep the sign with the delta T is negative 46.8 degrees Celsius. So then that negative needs to show up with our change in thermal energy. So yep, we are definitely over here. Exothermic is what your water's doing anyway. Now I think there's one more step here. A lot of times it's easier to talk about kilojoules instead of joules. So although it didn't say, what's sometimes useful is to take that joules and convert it to kilojoules with this relationship. 1 kilojoule is exactly equal to 1,000 joules. No uncertainty here. And units of joules will cancel, we'll be left with units of kilojoules. And it kind of makes sense. The whole scientific notation is kind of a pain sometimes. So now, instead of negative 7.38 times 10 to the 3rd joules, we have negative 7.38 kilojoules of energy. And that's it. So it's exothermic. Energy is being released by the water. So we would say that the change in energy is negative 7.38 kilojoules. Alternatively, we would say that 7.38 kilojoules of energy was released by the water. What you wouldn't do is, and that we don't usually do this down here. What we wouldn't do is say negative 7.38 kilojoules of energy was released by the water, because that's like a double something. Okay. Well, when we pick up here on Wednesday, this whole sign is really going to be important. I think I said that a few times. So we said if something's losing energy, it's exothermic, okay, and you're going to have a negative Q. And that brings me to where I want to stop. So we'll pick up here on Wednesday. So there will be, and we'll get through this, obviously, part. And so this assignment will be due on Monday. So nothing due on Wednesday, right? Yay. Okay, I'll let you out early again. Been watching those Cubs games?
Oh. I don't even, my grandpa's a Dodgers fan, so he's been texting me nonstop.
Trent.
He's like, well, it's going to be a good 4-game series. Trying to say
Is it
we're
the best
never
of
gonna
7?
win. Yeah,
Or-
it's 7, but he's trying to say they're going to win 4 in a row. I don't know, whatever.